All right. So we'll put off exam one till 2 weeks from today instead of a week from Thursday. We had these identities before. Sine of minus angle of minus goes out, cosine of minus an angle of minus goes away, and you get the same as cosine of plus the angle. We proved that in the unit circle. Then we'll define these four additional trig functions. And we'll say that by putting the angle in standard position, turning from the initial positive x-axis to here, there's theta. If you drop a perpendicular to the x-axis, and I say drop, if the angle's down here, you go up. It just means go to the x-axis with a perpendicular. And then close the triangle. You take the radius of the circle, the perpendicular that you make, and the line segment along the x-axis back to the center. We call this the reference triangle. Reference. And the angle inside the triangle always considered to be positive, regardless of which way theta went. The triangle angles are always considered to be positive. You don't need negative angles since they're all between 0 and 180 degrees. So this angle in here, taken positive, is the reference angle, we said. And we could use that to evaluate, we said, trig functions of any special angle whatsoever. We could just draw the angle, drop a perpendicular. If it's a special angle, this will be a special triangle, either a 30, 60, 90, or a 45, 45, 90, or we'll lie on an axis, and then we won't even need a triangle to figure out the sine and cosine coordinates. Also from those coordinates, for any special angle, we can figure exactly these four new trig functions. And if you think about it, what these are is 6 trig functions that give a ratio of 2 sides. For instance, the cosine of theta, if you look at this, it's a unit circle, so this is 1 radius. The cosine is this x coordinate, right? The x coordinate divided by 1. This ratio of the x coordinate, not the length of the side, to this side. The sine is this side, this y coordinate to this side. Tangent is the y coordinate to the x coordinate. The cotangent is the x to the y. Secant is this side to this side, and cosecant is this side to this side. All possible ratios of the 2 coordinates in R, if you like triangle with some of these marked as negative, is what the 6 trig functions are. So I guess that's why there's 6, is there's 6 possible ratios of the coordinates and the radius 1. All right, with those definitions, we deduce immediately some nice relations between these that will help us. That the tangent of any angle being y over x, well, y was sine, right? We said x is cosine, y is sine. Those are the two we had before. So this is sine divided by cosine. And then this part here, the names. And the cotangent being x over y. Well, x was cosine and y was sine. Which, without the proof step in the middle, called the quotient identities. So in addition to these even and odd identities, and this Pythagorean identity, and we want to memorize these, we said I already started, but I'll just start them again. There's a lot of identities in trigonometry, and they're very useful in later courses. You need them in calculus. They're quotient identities. Tangent theta equals sine over cosine. And I should put these names here. This one's called saying the tangent of theta. This one is called the cotangent. Theta. This is the secant of theta. This is the cosecant of theta. Now the tangent is then the sine divided by the cosine, and the cotangent, the cosine divided by the sine, will help us a lot. Because once we know the sine and cosine, we immediately know the tangent by this. We don't have to do any figuring. Furthermore, because these are all ratios of the three sides of this triangle, plus or minus, we have evidently reciprocal identities. Every trig function is a reciprocal of another. Right behind the monitor here. Let me know if I am. So the reciprocal identities are these. We notice the secant of theta, for instance, 1 over x, but x is the cosine, so it's 1 over cosine. Right? So it's a one-step proof true, like this. Secant is 1 over x is 1 over cosine. The cosecant of theta, that's 1 over y, but y was the sine, so it's 1 over the sine of theta. The cotangent of theta, well, it's x over y and tangent is y over x, so it's the reciprocal of tangent. And then every pair of reciprocals are reciprocals of each other as long as you don't have. So, like 2 1/2 are reciprocals, 2/3 and 3/2 are reciprocals. So if secant is reciprocal of cosine, it follows that cosine is the reciprocal of secant just by taking 1 over on each side. Here the secant is 1 over the sine, so it follows that the sine is also 1 over the secant. Cosecant. And then cotangent is 1 over tangent, so it follows the tangent is 1 over the cosine. And why do we call these identities rather than theorems? I'm going to memorize these two. I'm giving you a whole bunch of these. We'll stop giving these shortly, but there will be some more coming up. What's the difference between an identity and a theorem?
Is identity because like they're equal to each other? Like,
What we say is an identity is a theorem that's true whenever everything's defined. What can happen on some of these? You know, for instance, on a unit circle, suppose I took the angle 0 degrees like this, what would happen? Then the point here is 1, 0. And we say that the cosine of 0 degrees is 1. The sine of 0 degrees is 0, right? So now we know that actually some of these are undefined as a result. If the sine is 0, you have 1 over 0. 1 over 0 isn't defined, so the cosecant of 0 degrees isn't defined. Let's actually look at it on here. Cosecant 1 over y isn't defined. Similarly, the cotangent x over y isn't defined at 0 degrees. So there's different angles. When you're on some of the quadrantal angles, the angles that go between the quadrants, there will always be some trig functions that aren't defined because you get a division by 0 in the definition here. But you notice that this angle 0, the sine is defined. It's 0, the y coordinate. But cosecant 1 over 0 isn't defined, and so this one doesn't hold in the sense that let's say this one sine is 0, but cosecant is undefined. So even though sine is defined, you can't say it's 1 over cosecant because cosecant isn't defined. So these are theorems that are true whenever both sides are defined, but there are quadrantal angles between the quadrants where one side will be defined and not the other. So these are theorems. They're true whenever everything's defined. Right? Okay, so that's a whole slew of identities. And we've got almost all of them here. Maybe I should go ahead and put the last ones up just to get them out of the way. Let's say keep interrupting and overwhelming you with lots of these one at a time. Now we have the following results. There are actually even and odd identities for all 6 trig functions. I know we need some examples. Well, I'm going to put some identities first. We just define tangent to be the ratio of the y to x coordinate. the terminal right here. Cotangent to be x to y, secant is 1 over x, cosecant is 1 over y, and we get these nice relationships between the 6 trig functions. They're all reciprocals of one other trig function. The tangent and quotient can be written as quotients of reciprocal functions. And furthermore, we also have that the tangent of minus an angle, the minus comes out just like sine. It's an odd function. Remember we did even and odd last time for sine and cosine. The cotangent of minus an angle, the minus comes out. The secant of minus an angle, the minus goes away and it's the same as secant of plus the angle. And the cosecant of minus an angle, the minus comes out and we get minus the cosecant of plus theta. These are also even and odd identities. There's 6 of them, 1 for each of the 6 trig functions. What's curious to me, you know, you always respect symmetry, right? There's half the numbers are even, half the numbers are odd when you count off the numbers 1, 2, 3, 4, 5, and you think, you know, half the numbers are even and half of them are odd. If you pair 1 with minus 1 and 2 with minus 2, you'd think that half of these would come out even and half would come out odd, wouldn't you? But actually, 4 of them come out even and 2 of them come out odd, right? This is an odd identity. When the minus comes out, it says this is an odd function. We said it has a symmetry property from algebra. We'll go back and do that again later. This is even because the minus goes away. This is even because the minus goes away, but there's 4 functions that are odd and 2 that are even. Sometimes these things get so similar, it's harder to remember them. But just remember that cosine and its reciprocal, secant, are even functions, and all the others are odd. But it's kind of odd, isn't it? The 4 of them would come out to be odd functions and 2 of them even. You'd think half and half, you know, like half even numbers and half odd numbers. Anyway, that's the way it comes out. And it's easy to prove, though, if you don't like this. It must be wrong, right? It's not half and half. But the proof is quite easy, right? Here's tangent. I'm going to put just the proof of this first one, and you can see how to do the others, right? Tangent of minus theta. These proofs are good because when you forget, right, you can figure these things out, and you go, oh, yeah. It's always better when you can see why. At least it helps me. Tangent of minus an angle. Well, the tangent is sine over cosine of whatever angle you put in. So that's sine of minus theta over cosine of minus theta. But wait a minute, sine of minus theta, the minus comes out. So that's minus sine of plus theta. And cosine, the minus goes away. So the bottom is just plus cosine of theta. But sine over cosine is tangent with a minus out front. So this is minus the tangent of theta. There's the proof. The minus comes out. And you can do this for all 4 of these. You want to do one more? How about this one? Here's the proof of this one. And you can see these are all similar. The secant of minus theta. How can I prove this is an even function? Well, you say secant is 1 over cosine of the same angle. Right? Get rid of this. And now cosine is an even function. The minus goes away. So it's 1 over cosine of plus theta. Oh, but 1 over cosine theta by the reciprocal identity is secant, right? This is just 1 over x, and that's secant. There it is. That proves that secant is even. The minus goes away. The tangent is odd. The minus comes out. And so you do that for the other 2 also. But there's the last of them. These are all the ones we're going to need to know, except for 2 of them. 2 more Pythagorean identities coming up. And I think for the rest of this chapter. That's a whole lot of them. But now we can use those to speed up our additional computations with these new trig functions. Any questions before I erase all this? That's a lot of stuff before the exam. I know. Yeah.
Can you go over what you said about the quadrangle angle?
Oh, yeah. A quadrantal angle is an angle that comes out between the quadrants. We take this region here where x and y are both positive. We call that quadrant 1. This region here where x is negative and y is positive, call that quadrant 2. We give them Roman numerals. And here we call this where both coordinates are negative, quadrant 3. And here where x is positive but y is negative, we call that quadrant 4. V means 5 and I is 1. You put the I before the V and it's 5. Take away 1 is 4. And so if you take the unit circle at the origin, the circle radius 1 at the origin, you can take any angle in standard position theta and it has an x and y coordinate. But if that theta puts the terminal rate on an axis, so it's between the quadrants, we call it a quadrantal angle. And if you have a quadrantal angle, like say 90 degrees, right? Then what are the coordinates at that point? It's easy. Well, it's a radius 1 circle. And so this is the point 0, 1, because you went nothing horizontal and one straight up. And so you observe immediately that the cosine of this angle 90 degrees is 0. The sine of this angle 90 degrees is 1. We call that a quadrantal angle, but because cosine is 0, the secant, which is equal to 1 over the cosine, is 1 over 0 is undefined. So when you're on one of these quadrantal angles between the quadrants, sine or cosine is 0, one or the other. Right here, cosine is 0. If you're over here at the point 1, 0, then sine, the y coordinate is 0. On any quadrantal angle, one of these two functions is 0. And so you got to divide by 0 here, and one of the other 4 trig functions is defined. That makes sense, sort of, right? Because if you divide by x and x is 0, that's undefined. If you divide by y and y is 0, that's undefined. So these definitions are of functions that are only defined for certain x and y, just like square root of x. That function is only defined for x non-negative, right? It's still a function, but its domain is non-negative numbers. Just so here, the domains of these are angles that don't have division by 0. Any other comments or questions? I hate erasing it all.
So you said that the domain of all of these, what it is, unless it's over 0.
Yeah. And I'm going to be more specific about that coming up. For now, I'm just trying to get all this up here so I can do some of the evaluations of these trig functions, and then I'll come back to what the domains and ranges are of these things, function theory. Yeah, those are actually the important questions. All right, any other comments on this? Feel like you sort of understand what the 4 new trig functions are? They're just ratios of x and y in the same unit circle, just like this x coordinate was cosine, this y coordinate was sine. These are all ratios of the two x, the x and y coordinates and the hypotenuse of the triangle. There's one. Every one of those. Okay. Well, we're going to erase this one. And now we have a whole bunch of problems in the section like this. Here's one here. What was the theta of the angle 7 pi over 3 radians? Fine. Hey, we did some of these last time. This is to remind you, then we'll get on to the other 4 trig functions. What is the sine of theta? What is the sine of 7 pi over 3? And you'll probably get a different angle in your homework. That's why they put if theta equals to the first part, they just change the rest of it. All right. So what's the sine of 7 pi over 3? How do we find that out? I'm going to erase these. These, despite that there's a definition, are not as important as these because usually we evaluate the trig functions using these instead of these. That's why I said, even though you have to know these are not as important. All right, so what if the sine of theta, if the angle of theta is 7 pi over 3, how do we evaluate the sine? Remember that from a long time ago? You tried some of the homework. What do I do?
Have full rotation, so minus 6 pi over 3.
Yeah, good. I'm glad some of you did at home. Yeah, you take the angle and you write it, you break it up in any way you want so you can sketch it well. The common thing to do is take this at 6 pi over 3 because that's 2 pi. This is one rotation, so you pull out the whole rotations, and then you take the remainder, pi over 3. Then if there's a straight angle left, you take that out. If there's a right angle left, you take that out, and then you get a fraction of a right angle. This is a fraction of a right angle, right? A right angle is pi over 2. This is pi over 3 that's left. Less. This is actually 2/3 of a right angle. You start. This was the equivalent of 60 degrees. That's why you want to memorize them. You don't want to convert every one of these. You just want to remember this is 60 degrees, 2/3 of a right angle. So I have a rotation and 2/3 of a right angle. I can break up the first quadrant into 3 equal parts. Here's my rotation. Here's my 2/3 of a right angle. And what I do is I put the unit circle here. Right? And This is the terminal ray for this angle in standard position, right? So the coordinates of the point are the sine and cosine. I drop a perpendicular to the x-axis, taking the radius, the perpendicular, and the line segment back to the origin. I say this is the reference triangle. This is the reference angle. What is it? It's just this, yeah, 60 degrees, just pi over 3, right? So whatever the angle inside the triangle is, not the original angle, is the reference angle. So this is the reference. When they ask you in the homework, what's the reference angle? It means the angle inside the triangle. It's always positive or 0. Non-negative, I guess you'd say. Okay, so there's the reference angle. What's the sine of 7 pi over 3? It's the coordinate. It's the y coordinate at this point, right? That's the way we defined it. So if we look at this now, this is one of the special triangles, and this is why we memorize them. 30, 60, 90 triangle has one. If you put 1 on the hypotenuse, it has these two other sides, 1/2 and square root 3 over 2, right? This was one of those two special triangles we memorized. We memorized them with the 1 hypotenuse because then they fit in the unit circle. And now you know what these sides are. The coordinates of this point are plus 1/2 because we went right, plus square root 3 over 2 because we went up. And so those are automatically, by definition, the cosine and sine of whatever angle puts you there, right? You just take the terminal ray of that angle, and that determines the cosine and the sine, right? So we know those, and one of the nice things about being in the first quadrant is if the terminal ray winds up in the first quadrant, and when we say what quadrant is the angle in, we mean what quadrant is its terminal ray in. In the first quadrant, the coordinates are both positive, and so all 6 of those ratios, y, x, and 1, are always going to be positive. So that's a nice thing to know, that all 6 trig functions are positive in the first quadrant here, with x and y are. There's cosine and sine immediately. Remember, cosine is the first coordinate, sine is the second. And now from these other relationships that we wrote, we can find the other 4 trig functions immediately. So here's the second part of that question. This one is the second coordinate is square root 3 over 2. And on the test, when I say find the coordinates, I want you to find the exact answer. Leave it in terms of square root 3 and 2. On some of the homework, they have you put it in decimal form. On the test, I'm generally going to ask you for the exact coordinates. All right, so on the homework on the test, there sometimes you have to figure out square root 3 and 2, but unless I say round, leave this exact answer. In fact, I'll say find exactly. I'll usually specify that on the test. Find exactly this. Then you want to write this instead of the decimal because the decimal is the rounded version. All right, now find B. Find exactly the cosine of the same angle, 7 pi over 3. What's that? That's just the x coordinate. It's exactly 1/2. If you do your calculator, you'll say 0.5, and that actually is an exact answer because with printing zeros forever, right, this is exact, unlike this one. You don't have the rest of the decimals. So you could put 0.5 on this one, but don't put 1.732 here, wherever you round it, it's not exact. All right, but now we have 4 more trig functions, right? We did this last time. We can find all 6 trig functions at any angle. C, for instance, what if I want to know the tangent of 7 pi over 3? How about that? We can say it's y over x, and that works well. Or just as well, once we have the sine and cosine, we can say, oh, it is sine over cosine. So it's the same thing because sine is y and cosine is x, right? So you can say y over x, or what you just found, sine over cosine. So we'll say square root 3 over 2 divided by 1/2. There's the tangent, y over x or sine over cosine, either one. Now, here's where you have to really get good at your algebra. I told you be good at algebra by the time you get out. What does that come out to be? Yeah, it comes out to be square root 3. You can do it multiple ways, right? You can say quotient of quotients. You take the top one times the reciprocal of the bottom. I won't usually spend so much time on algebra, but it's the top one times the reciprocal of the bottom. Turn it upside down. And so then you can say it's top times top, this times this over this times this, 2 square root 3 by multiplying the other order over 2 times 1. And what you notice is it's top times bottom over middle times middle always when you do this. So I don't usually bother to do this, write it as top times the reciprocal of the bottom. I usually start top times bottom over middle times middle, and that's y, right? And then I notice in this case, these twos cancel, and she's right, you get square root 3/1 or just square root 3. So on tangent, what you want to get here is square root 3, but you notice when they have the same denominators, not when one has a denominator that matches the numerator of the other, right? But when the bottom is the denominator of both things, you can cancel them and just say this is square root 3/1. I can go right to here. So on your test, just go right to here, but just be careful you don't cancel a numerator and denominator. If this was 2, you can't cancel it. Bottom with the bottom, you can cancel it, or the top with the top. So tangent is exactly square root 3 ratio of y over x. All right, so there's the third trig function. And this one now, cotangent is x over y. So I could write 1/2 over square root 3/2, but there's an even easier way to do it. Do you see it? Here's the big trick, and the reason I wanted to write these ahead of time is once you have the first three, sine, cosine, and tangent, the other three easy, right? You've got reciprocal identity. Secant is 1 over cosine, cosecant is 1 over sine, cotangent is 1 over tangent, just by their very definitions, right? It's just 1 over x, 1 over y, and x over y, or 1 over y over x. And so now by reciprocal identities, I have the last three just by turning these three upside down. The cosecant of theta, right, was 1 over the sine, so it's 1 over square root 3/2. Well, what's that? Again, if this is on the bottom, you just turn it upside down, it's 2 over square root 3. I will take this for an exact answer on the test if you want to write it like that. But what your algebra teachers say is the right result.
Square root of 3.
Yeah, so if you look at the back and like you're doing some of the problems in the book, and you go to look in the back to see the answers, right? There's answers to, it's all odd ones, or anyway, a lot of them. They multiply top and bottom by square root 3, so it's 2 square root 3 over square root 3 square root 3. That's the same quotient, right? Multiplied top and bottom by the same thing. But now square root 3 times square root 3 is 3, and you've rationalized the denominator. You got the radical signs out of the denominator, and just have a number that's not a root. So this is what the book will put in back, the rationalized form, where all the square roots are out of the denominator. But this is shorter to write. So a lot of higher mathematics people, I think I said this last time, write it this way. But this is the way all books put it, because if it looks the same, it is the same once they're rationalized. Where here, these two don't look the same, but they are equal, right? So higher mathematics, we write it like that, just figure if we rationalize, what will we get? And the book will put it like that. And so either answer is good on the test for me, as long as this is simpler. If this is more complicated, then you have to simplify it. All right. So cosecant is just 1 over the sine. You flip the sign upside down, right? Instead of square root 3/2, you get 2 over square root 3. Now secant theta is 1 over the cosine, but the cosine was 1/2, right? Cosine was 1/2. 1 over 1/2 is its reciprocal 2, right? You just turn this one upside down. And the cotangent of theta is the tangent of theta. So you take 1 over square root 3. Tangent was square root 3. And again, you can leave it like this, because that's simple, or you can multiply top and bottom by square root 3 and rewrite it as square root 3. Either one of these is good. So the first principle here on the new trig functions is, I should put this at the star. We can now find exactly, not just the sine and cosine, but we can find exactly in terms of square roots, all 6 trig functions, not just the 2, of any special angle. That's any angle that's a multiple of 30 or 45 degrees. Like too crowded here. So this is a very important principle too. Wants to be able to do that, and you do it exactly this way. You sketch the angle, make the reference triangle or the quadrantal angle, and then from the triangle or the coordinates in between the quadrants, you figure sine and cosine. Once you have sine and cosine, the quotient identity for tangent and the 3 reciprocal identities evaluate the other 4 trig functions. Easy, right? Just kind of have to know the procedures, like baking a cake or something, right? It's gotta know what you're doing. Put in the eggs and mix it up, put in the sugar and mix it up and put it in the oven and so on. We just gotta do those things in order. Sketch the angle. Draw the reference triangle or the quadrangle intersection point. Find sine and cosine, use the identities to get the other four. And that's the easiest way. You can get them all from the X and Y coordinates if you prefer memorizing the first part. But how much easier to do this, I think. All right, so now I can finally erase these now that I got to use them. Okay. Now, let's see. There's a couple of these in here. I think I'm gonna have to delete in the upcoming section, not this section. They seem to have some questions that aren't even in the chapter, and I'm not sure why they're there. But we'll get that fixed. Here's another one. This is the next principle. So the next principle is if you have the value of one trig function instead of just the angle, right? So there we said if you have a special angle, you figure all 6 trig functions. Instead, if you have the value of a trig function, not its angle, any angle whatsoever, if you know the value of one of the 6 trig functions, and can figure by the information given the quadrant, by that I mean the quadrant of the terminal ray or the quadrant of the angle, the same thing. You can figure all 6 trig functions. Find values similarly, all 6 trig functions. There's only 6, although there's some other ones that are occasionally remotely defined. Every trig function only does, every normal trig book only does these 6. All right. I'll show you on the screen some of the other ones. All right, so you can do all 6 trig functions with a special angle. You can do all 6 trig functions if you know one and a quadrant. So here's an example of the homework I want you to be able to do. Try these when you get home, because these are not real far away. They do. Example, this one, suppose that the sine of an angle, we don't even know what angle it is 3/5 with angle theta in quadrant 2. I'll write Q2 for brevity here. Find the other trig function values. Find the values. Other 5 trig functions of theta, whatever theta is. How about that? We'll use t instead of theta. All right, how do I figure those? Here's the trick when you're given sine or cosine, all right? Immediately, if you know sine or cosine, you know the other one. From the Pythagorean identity, I wrote at the beginning. We did this last time. Hopefully you remember. I'm going to abbreviate this just to save my hand a little. From the Pythagorean identity, solve for cosine theta. Remember seeing that right at the end? Everything at the end is always forgotten. But I really prefer 50-minute classes to an hour and a quarter class. What does the Pythagorean identity solve for the cosine theta? Sound familiar? No? Let me put it back up again then. Just say recall, this is an aside, you don't have to write it again if you don't want. The Pythagorean identity was the sine squared plus cosine squared equals 1. That's called the Pythagorean identity because it comes from the Pythagorean theorem, right? If you draw any angle, I'll draw in the first quadrant for simplicity. but it works in every quadrant. And you put cosine theta as the x coordinate and sine theta as the y coordinate, and this is 1 because it's a unit circle, right? What's the relationship between sine theta and cosine theta? We wrote it at the beginning. Oh, by the Pythagorean theorem for this right triangle, you got the perpendicular. This squared plus this squared equals this squared, right? So sine, the sine of the angle squared plus the cosine of the angle squared is equal to 1. From this triangle, it's a Pythagorean theorem applied to this triangle in a circle. That's why it's called the Pythagorean identity, right? Pythagorean identity. Now, this notation is cumbersome, writing those parentheses all the time. So what do we do to simplify that? We say, rather than write parentheses all the time, I'm going to write sine squared theta, and this is notation for this. So you don't have to write the parentheses. So all this is on the next line is a change of notation. Sine squared plus cosine squared equals 1, and this means this, right? So that's the Pythagorean identity written in. These are both the Pythagorean identity. This is the one written in the notation. Save parentheses. Now, how do I solve that for cosine theta? This gives by subtracting sine squared from both sides, that cosine squared. These proofs are really useful because once you see the proof, it's much easier to remember. I can never shove all those words in foreign languages down my throat and keep them. I always forget them the next day. But if I see why it works, then I remember it much better. All right, cosine squared is 1 minus sine squared by subtracting sine squared from each side, right? And then I just square root, right? Cosine theta. Cosine squared is this, then cosine theta must be square root of this. Except what? Missing. Now, plus or minus. Right, if the square of something is equal to a non-negative number, the original thing must be plus, can be plus or minus the other number, right? Like when I write x squared equals 4, x can be plus or minus the square root of 4. This notation means the non-negative number whose square is 4, so it's 2. So x can be plus or minus 2. And this means the non-negative number whose square is 1 minus sine squared. And so it can be plus or minus that, and there's two solutions. So I call this the Pythagorean identity solved for cosine. You need to know that because even though this is the important identity, I'm going to start here to save doing these two steps over and over all semester. And we have one more from here. If we subtract cosine squared from each side, we got sine squared equals 1 minus cosine squared. And then when I square root both sides, square root of the square is a sine. This one implied this one implies this one. The sine theta is plus or minus the square root of this side. If the square of the number is this, then this number is plus or minus the square root of this. So there's the Pythagorean identity solved for sine. And so these two are just derived out of this one. And this means implies. If this is true, then this is true. That's what it means. All right, so if I'm given sine, the first thing I do is I say, I immediately know cosine. Instead of going through these two steps, I just write immediately cosine theta is plus or minus the square root 1 minus sine squared theta. The Pythagorean identity solved for cosine. Tell me when it's confusing here. Man, wait a minute. Is it plus or minus? How do I know?
It's positive because it's in quadrant.
That's negative because it's in quadrant 2. Yeah, what you do is you say theta is in quadrant 2, then somewhere over here, going in the terminal rays over here. On the unit circle, then, xy, recall, is cosine first and sine second. So cosine is the x coordinate, and it's negative, right? You drop the perpendicular, the x coordinate is negative. Y coordinate is positive. So sine is positive, but cosine is negative. So I'm going to choose the minus sign. But you can picture this in your head. You don't have to draw it. Quadrant 2 says I have to choose the minus sign. Now, sine was given as 3/5, so this is minus the square root of 1 minus. Sine squared theta again means take the sine of theta and square it, right? That's just notation. So it's 3/5 squared. Or 9, let's write that in there. 3/5 squared. Sine squared means take the sine of theta, 3/5 and square. And now you have fractions to do here, right? This is square root of 1 minus 9/25. What's that? How do I subtract? A whole number minus a fraction. I have to put them over a common denominator. Algebra, you're gonna be experts, right? So I write 1 is 25 over 25. Common denominator, like to subtract them like it's 25 slices of pizza out of 25 and a whole pizza less. Then I eat 9 of the 25. I have 16 of the 25 left, right? And so you subtract the numerators over the common denominator. Now you take the square root of 16 is 4 and the square root of 25 is 5. Cosine must be minus 4/5. There it is. Now remember from the last example, once you have sine and cosine, you have all 6 easily. What do you do next? Once you have sine and cosine,
You use tangent.
yeah, just like last time, tangent is sine over cosine, so I figured that one. It's, let's see, 3/5 over minus 4/5. And now the 5's cancel because they're both denominators. I get minus 3/4. There it is immediately. How about that? Easy. What's the secant? The reciprocal identity is 1 over the cosine, right? So by the quotient identity, tangent is sine over cosine. By the reciprocal identity, secant is 1 over the cosine. Is just turn this one upside down, minus 5/4, right? That's how you take 1 over, you just turn the fraction upside down. Cosecant, see how much better everybody's getting in algebra already, if you weren't already. Some of you were very good. Cosecant is by the reciprocal identity 1 over the sine or 1 over the y. But the sine was 3/5, so this is 5/3. That one upside down. There it is. Right? So once you know sine and cosine, you take their quotient to get the tangent. You take their reciprocals to get the cosecant. Oh, and secant, cosecant, and then we have cotangent is 1 over the tangent. 1 over minus 3/4, or we could take its cosine over sine, either way. You can use cosine over sine, or you can use 1 over tangent. But the reciprocal of minus 3/4 is minus 4/3. You turn it upside down. There it is. There's all the other 5 trig functions, right? 1, 2, 3, 4, 5. Easy, right? Math always builds, right? You come in the first day, it makes sense, and then the second day, it kind of makes sense, and the third day, if you didn't do your homework, it's all Greek letters. So now, if that, any questions on that one before I go on? Because the next one's going to be a little bit harder. So there I'm given the sign, I can find the other trig functions. Here's, let's see. Some of these are kind of repetitive, I'm afraid. There we go. There's a harder one. I'm gonna come down here to 21. Do this example. Suppose instead of being given sine, we're given tangent. Tangent equals 5/4. By the way, you're gonna see some common ratios in here. You notice in these last these last 6 trig functions, every ratio just had 3 numbers in it, 3, 4, and 5. And so every one of these 6 things was a ratio with 3, 4, or 5 on the top and bottom, 2 of those 3 numbers, and some of them had minus and some of them didn't. But that's going to be a common theme here. What it's doing is it was taking an angle in quadrant 2 where you had a 3, 4, 5 right triangle. You could a 1, 3/5, and 4/5 triangle. Let's see, it was cosine. Sine was 3/5, so I guess it's over here. It was taking this angle where this is 3/5, the y coordinate is sine. Cosine came to be minus 4/5. I'll call this 4/5, but it's in the negative direction. I'm running the side lengths here. And so it was using this triangle to figure everything out. You could just easily say tangent is y over x, cotangent is x over y, and figure out all those things. Use the coordinates though, not the side lengths, to figure the quotients. And what it's doing is it's taking a scaled down version of the 3, 4, 5 triangle. It's just scaled it by a factor of 5. So it's 1/5 of this length, 1/5 of this length, and 1/5 of this length. So it's a 3, 4, 5 triangle scaled by 1/5. A lot of these you'll find is the same thing, and you'll get ratios of the same three numbers because they come out of this triangle that's got nice whole number sides. In practice, when you go into real life and do these things, hardly ever do you get whole number sides. We call those Pythagorean triples when you get whole numbers on the sides. This squared plus this squared equals this squared, and they're all whole numbers. But this is going to be the same three numbers on this particular one. You might get different numbers. Suppose tangent theta equals, so that gives you a little hint here. That's going to make this easier. Suppose tangent's 5/4 and the sine of theta is less than 0. So instead of being given a quadrant, I'm told that the sine of theta is less than 0, and I have to figure the quadrant. Fine. The first one is, what's the sine of theta? How can I do that from tangent? There's a trick here. Go ahead.
Tangent is sine over cosine.
Yeah.
Tangent is
It's trickier than that. Yeah. So this isn't sine and this isn't cosine because it's not a point on the unit circle. Again, it's a bigger triangle. They call this the XYR diagram in some trigonometry books. This one doesn't bother to do it. If you treat this as y over x, then you're going up to the point y equals 5, x equals 4. And saying, oh, the tangent of the angle is the ratio of this side 5 to this side 4, but really the sine and cosine are the corresponding point on the unit circle. You have to divide this by 5 and say this is 4/5. I'm sorry, divide this by, oh, this isn't even, I thought this was going to come out 3, 4, 5 right triangle because the 5 and 4, but it's not. Never mind. So this is actually going to have some coordinates here that aren't whole numbers this time. And it's going to be a shorter length. So the actual sine and cosine are not going to be 5 and 4 because what you have to do is first scale it down to get the point on the unit circle. So this could be, see, this is 5 and this is 4 on the big triangle. But the actual point on the unit circle in the same direction, this is your theta here, is what? What you can do is divide by this length, right? If you divide by this, if you scale each side by this length, you get the point on the triangle that has unit length, right? So you scale this to be 1 over its length as long as the scale these the same. In other words, you root sum square these two numbers from square root of 4 squared plus 5 squared is square root of 41. This is going to illustrate how you usually get square nasty numbers in these. We also have, by scaling the triangle down, see this side is square root of 41 is what's happening. By scaling it down to the unit thing, then we scale all three sides of this by square root of 41. And we get, actually also the tangent theta is 5 over square root of 41 over 4 over square root of 41. I multiplied top and bottom by 1 over square root of 41. So it's the same quotient, right? I multiplied top and bottom by the same thing. But now this is the sine and this is the cosine. Or there's one other possibility. It could be minus the top over minus the bottom, and we get the same quotient. Which one is it? This is where you need the quadrant. Even the trig function doesn't tell you enough. You need the quadrant, or at least to know this. This tells you the quadrant. If tangent is positive and sine is negative, this actually tells you it's quadrant 3. Right? But what happens is if sine is negative, that means your angle has to be around here or around here in quadrant 3 or 4 to get a negative y coordinate, right? Here's the unit circle. So it has to be in quadrant 3 or 4. But for tangent to be positive, that's y over x. You have to have x and y of the same sign, so it has to be quadrant 3. You kind of figure that out. That if sine is negative and tangent is positive, the ratio of y to x, then that has to be quadrant 3. So we'll put that over here, or you can say sine is negative, so it can't be this one, right? This must be the sine of theta. This must be the cosine of theta. Here's what you do when you're given tangent or cotangent. That's the hard case. Divide top and bottom by the root sum square and consider both cases, plus and minus. And whichever one it comes out to be, the top one's now the sine and the bottom one's now the cosine because it's the same triangle scaled with the sides by square root of 41, so it's on the unit circle. All right, so now I've got immediately by dividing by the root sum square that sine theta is minus 5 over square root of 41, the numerator divided by the root sum square, and cosine theta is minus 4 over square root of 41, the denominator divided by square root of 41. And you can rationalize these if you want, but I think I'd rather leave them like this, and I'll show you why in just a second. Like rationalizing is great for your algebra teacher, but who rolls over your grade if you don't rationalize, but I roll over my grade if I having to rationalize this, because now what happens at the next step? Suppose I want to find cosecant theta, right? That's the reciprocal of sine. I write it as minus square root of 41 over 5. Alas, if I rationalized, then I'll get the square root on the bottom, right? So I just leave this on the bottom, and then it comes out on the top up here. And then similarly, right, because this is 1 over the sine, you turn it upside down. The secant is 1 over the cosine, so you turn this one upside down and get minus square root of 41 over 4. And what's the cotangent? That's the easiest one. If you get nothing else, get the cotangent. That one. The tangent upside down. So I just take this upside down, 4/5. But these three are just the reciprocals of the other. So once you get the sine, cosine, and tangent, you just turn them upside down and get the last three. How about that? And if you didn't rationalize, it's easier. So, but you can rationalize too, and you want to do that to check the back of the book sometimes. You know, if it makes it simpler, then you got to rationalize it. It does for these. There it is. If you got sine theta, I found sine theta. That was A, and then B, find cosine theta. C, find cosecant theta. How about D, find secant theta? And E, find cotangent theta. So you can find all 5 of the other trig functions.
What would you consider as too big, so we would have to rationalize?
It's not a matter of being too big. It's a matter of if I put 2 over square root 6 or something like that. What you can do is you can rewrite this as square root 2, that's 2, right? And 6 is square root 2, square root 3, and so these cancel. It'd be better to write that as square root 3/3 or something like that. You have these kinds of dilemmas. This is actually probably okay, but generally you want to cancel these things that you cancel. It's more evident if you have 2 over square root 12, right? This one I will kind of point out for sure, because what happens is square root 12 is square root of 4 times 3, right? But square root of 4 is 2, and then square root of 3 doesn't reduce. And so this square root of 12, you rewrite it as 2 square root of 3, the 2's cancel, and you have 1 over square root of 3. So this is okay, but this is not, because it's not as, you haven't simplified it. So if it's not simplified, you have to do that. But once it's simplified, you can leave the radical down at the bottom if you want. You don't have to rationalize it from there. Now you can write this by rationalizing it square root of 3 over 3 if you prefer, because that's what all American books do. Just for comparison purposes and algebra.
Would you want us to write 1 over square root of 3 or square root of 3?
You can write either one of these. Don't write this because something will cancel. That's not simplified. You can write this or this. This one's simpler and this one's rationalized. They're both good. Don't put a decimal because that's not exact, unless I say round. If I say round, then write the decimal. Otherwise, write the exact answer. Okay? All right. So that's actually the hard case. There is one more case here, and I don't. There we go. This is 22. Got to do enough of these that feel comfortable from the homework. Come by and ask me questions. I am here 11 to 11:50 today, and I'm here again tomorrow afternoon. Afternoon hours been actually popular for people coming in. Plus, I should mention the tutors at the end of the hall on the right, the last door before you go to MCS 100. Their hours are posted on the glass right outside the door before you go out. They have lots of hours. They're here even in the evenings. I'm here in the evenings actually on Mondays and Wednesdays. But they're in the evenings all week except Friday. And you can see what their hours are there. They're in the mornings, afternoons, and evenings. I haven't seen a lot of lines. It's a computer terminal room, so look for whoever's has a tag on that says tutor hanging around their neck, and go ask them. The other people are students like you trying to figure their homework. But every time you get stuck on the homework, you just wave at the tutor and they'll come help you. Some of them took trigonometry here too and remember it well. So, but they're upper division students and graduate students usually. All right, so here's another example. If cosecant is 11/10 and 0 is less than theta is less than pi over 2. Find, let's just say find the other trig functions. How do I solve this? We said if you're given sine or cosine, use the Pythagorean identity to find the other one. Given cosine, you find sine. Given sine, you find cosine. Then you find tangent as the quotient, and the other three is reciprocals, right? If you're given tangent, you divide top and bottom by the root sum square, consider the plus and minus cases. To get sine and cosine, and then you get all the four from those again. What if I'm given cosecant or secant, one of those two? That's the last step. Yeah, immediately if I know cosecant, since I have one of those reciprocal identities, sine theta is 1 over cosecant theta, is then turn this upside down 10/11. Now I know sine, and this is quadrant 1, right? That tells you quadrant 1. Now I have sine in a quadrant, just like the first problem. I just find the other four from that. So given secant or cosecant, use the reciprocal identity to find sine and cosine, and then you do it just like the first problem. Now I know cosine is what? Pythagorean identity, solve for cosine, right? Square root 1 minus sine squared, right? We don't want to write sine squared plus cosine squared equals 1, subtract and square root every time. We just start with this step, right? But it comes from sine squared plus cosine squared equals 1. Is it plus or minus? Plus, yeah. Quadrant 1, everything is plus, right? All fifth degree units are plus because y and x are both plus. So I take the plus for quadrant 1, and I know the angle between 0 and pi over 2, a right angle, is first quadrant. All right, so this is plus the square root of 1 minus 11/10 squared. And once again, this is not from a Pythagorean triple. There are lots of Pythagorean triples. If you look, Google Pythagorean triple and look under Wikipedia sometime, it's very interesting. But like there's this one, 5, let's see, 12 and 13. 5 squared plus 12 squared equals 13 squared, you get whole numbers. But there's not all that many, 7, 24 and 25 is a Pythagorean triple, but most numbers, if you put two sides, the third one will be a whole number. So this one is not going to be a whole number. It's not a Pythagorean triple. But we can still figure it, right? This is square root of, well, let's see, 11/10 squared is 11 squared, 121 over 10 squared, 100. It will behoove you to memorize some of the squares through about 13. That's about as big as they go in the textbook problems. And so what do I need for to put for instead of 1?
Wouldn't it be 10 over 11?
Did I write it wrong? Oh, yeah, I was looking at this one. Thank you. 10 over 11. I'm glad somebody's awake at the end. 100 over 121. Yeah. So I want to write 1 with the same denominator to be able to subtract. So it's 121 over 121. Now, subtract the numerators, you get 21 over the common denominator 10, or 100. This square root, the bottom is a square, so you want to call that 10, but the top is not a square, and it doesn't reduce, right? Square root of 12 we can reduce because it's, right, square root of 12, square root of a square times a non-square, so you can reduce it to 2 square root of 3, but this is just square root of 7 times 3, two numbers that aren't squared, you just leave it the way it is, right? Doesn't reduce anymore.
Isn't the bottom 121?
Oh, golly, yes, you're right, yeah, 121. I still have that in my mind. Yeah, so it's 11. Good thing I have you guys here. All right. So yeah, square root of 21 over 11. There's cosine. Once I have sine and cosine, I have all 6 immediately, right? Look what I do. Tangent is sine over cosine by the quotient identity. So I take, let's see, 10/11 over square root of 21 over 11. The 11's cancel, they're both denominators. I get 10 over square root of 21, which I can rationalize if I want to check the plus. Then the last three are reciprocals, right? Secant, well, you can do whatever order you want. Secant is 1 over the cosine. you turn this one upside down, 11 over square root of 21, right? 1 over cosine. I never know what the angle is, but if I know one trig function in a quadrant, I've got it all. Cosecant is this, the sine turned upside down, so it's 11/10. And then cotangent is the tangent turned upside down, so square root of 21. There we go. I've got all 6 trig functions. And look, it's the same thing. So within plus or minus, they're all just the 3 numbers, 10, 11, and square root of 21, if you don't rationalize it. Because it's 3 sides of a triangle and inside the circle. I mean, the idea is that you're in the first quadrant here, and you can make a big triangle. This is what's in some books. Where this is 10, this is 11, now this is square root of 221. Let's see. What do I do this? Oh, I know, I drew that wrong. It should be 11 here. 11 here, 10, and square root of square root. Yeah, there it goes. 10, and so there's the triangle. It's making, there's the triangle it's coming from 11, 10, 11, square root 21. And if you take the corresponding unit circle, or you divide by this distance from the origin, 11, you divide everything by 11, then this point becomes the cosine square root 21 over 11. And the sine is this one over the length of the hypotenuse, 10 over 11. And then you get that. So you can also do it that way. They call it the XYR diagram. But I just wanted to show you geometrically why you get the 3 numbers. It's coming out of this triangle and scaling it to the unit circle. But with these 3 sides. Square root 21 over 11, 10 over 11. What? Well, that should get you through most of this, except there's some other tricky questions here. That they take those other identities we put up there. Actually, can't get this to stay in place. Well, suppose I said this. Well, sometimes they're testing on some of those other identities. Oh, the sine of u, some angle, is 3/5. I'll give it the same name as they had in here. And cosine is negative. We did this before. Find the cosine of u. What's the cosine of u? It's plus or minus square root 1 minus sine squared. Right? Same as before. Cosine is negative, so you take that and you get, I'll just do it quickly here. You actually turn out to get 4/5. That's what we did in the first problem. Then you're supposed to find tangent u. Well, that's sine over cosine, right? Is 3/5 over 4/5, and you can cancel the 5s and get 3/4. And again, it's the same 3 numbers, 3, 4, and 5 coming out in these triangles. But now the problem goes on and says, well, what's the sine of minus u? How do I figure out sine of minus the angle? Way back to the beginning, an hour ago. Remember the minus, all the functions are even or odd. Either the minus goes away or the minus comes out. Sine was odd, the minus comes out. So there's the odd identity. Most functions are neither even nor odd. You'll find out in algebra, but every trig function is either even or odd. Cosine and its reciprocal are even. All the rest of them are odd. So minus sine u, since sine u was 3/5, is minus 3/5. That's the sine of minus the angle. Then they say, well, what's the tangent of minus u? How about that? Well, tangent is odd, the minus comes out, minus the tangent of u gives me, well, that was minus 3. Oops, I got the wrong one here. Sine was, it should have 3/4 for tangent. 5's cancel, you get 3/4. So tangent minus u is minus 3/4. And now the hard ones at the bottom. That'll leave us something interesting when we go here. What is the sine of u plus pi? Oh. I wish they wouldn't have asked this yet. There's another section where this will be, we're going to cover where this will be easier. What's the sine of u plus pi? There's a couple problems in here I might have to delete because they're getting too hard, but here I have sine is positive and cosine is negative. So what quadrant am I in? It says y is positive and x is negative on the unit circle. So x negative, yeah, I'm in the second quadrant over here somewhere. I don't have to draw the angle exactly, but whatever theta is, it's in here, it's the second quadrant. Now, what if I add pi to that? That means you add a straight angle and you go the opposite direction, right? So here's theta plus pi is the opposite direction. What are the coordinates of sine and cosine here? You know, there's the negative of each other. So this one, sine of u plus pi is just minus the sign that you got over here, right? It goes straight across, and this is minus the y coordinate you got here, minus the x coordinate you got here. It's minus the sine of u again, is minus 3/5. So you can figure things like that. If you put the opposite one, that just makes the sine and cosine minus each other. And then the tangent of u plus pi. I don't think this is the same order of letters as they have in the homework, so be careful. But what's the tangent of u plus pi? Again, opposite direction. X and y are both minus each other, but the ratio of y to x is the same, right? Tangent of u plus pi is minus y over minus x from the first point, x, y. That's right, this one is then minus x minus y. And so it's the same, it's y over x, it's tangent of u, which was 3/4. So when you add pi, tangent's the same, but when you add pi, sine picks up a minus sign. But that is time to go. I better shut up. You guys don't give me bad ratings. I those homework, so big questions next time, all right? Or combine 11. See you again this morning. Okay, good day. Oh. Okay, yeah. Oh. Yeah. You have to have that. Just however you can. Card or the gift card didn't work. Yeah. Yeah. Don't find a public laptop here, you never know. Yeah, yeah. I have to have it for the course. Probably so much trouble for you. I'll send you some more copies. Okay.
I'll try that and then I'll let you know, of course.
Yeah, I hope you didn't get too far behind.
Yeah. Yeah.
Catch up. Real.
Yes, there is. Thank you.
Yeah, okay, thank you for coming by.